we're ready to go. Okay, so today I'm going to go over some of the math that we need for the homework. And what this is going to be about is stuff that you've had. In fact, you had it sophomore year, or maybe even in high school. I had some of this in high school. And, but the idea is not so much for you to tune out and say, okay, I know this, but rather to see what's a little bit different about how we approach it or what we think's important. And what you're going to find later, I always find that this first lecture, people think, oh, yeah, you know, a little bit faster, I can do this. But then later, they'll have some trouble, and it'll turn out that what I'm doing is I'm using a concept from this first lecture. And that's why I go over it, but it's always a little bit of a balance, you know, go over it, you know, try to keep you engaged. So I'm going to kind of speed through it, and then we're going to do some of the calculations so that you can see what I'm talking about. All right. So the basics of vector and tensor math are that there are these three entities: scalars, vectors, and tensors. All right. Now, a scalar is a quantity that has magnitude only. So that's what I've got here. Examples are temperature, speed, time, density. So for instance, density, there's no direction as there is with velocity. It's just a magnitude. It has units, but that's not relevant to us. The idea is it has no direction. Now let me contrast that with the term variable or constant. Scalars can be constant or scalars can be variable. The word scalar refers to the fact that they have magnitude only. And then you learned these way back, maybe even in middle school, that there's this commutative law, associative law, and distributive law in operating with numbers, essentially. And these are just algebraic symbols of numbers. Now, of course, that contrasts with the vector. So a vector is a mathematical entity that has magnitude and direction. And so our favorite vector is velocity, and our second favorite vector is force. And in my book and in this class, we denote a vector by this underscore on the bottom or by this little caret on the top of a unit vector. All right. So a force has magnitude, a vector has magnitude and direction. And again, a vector may be constant or variable. When we get to taking derivatives of these various quantities, it'll matter whether they're constant or variable. But the point is that I think in our colloquial speech, constant and scalar sound like the same thing. And I'm going to use them very precisely to mean different things. A constant is something that never changes. A scalar is something that has magnitude only. So the force of gravity, which is a vector, is a constant. But the force on this tabletop with me leaning is a variable. If I allow it to be, if I change the direction, then the force that I'm applying is varying in position. So now going back to my nomenclature here, we have magnitude of a vector, which is denoted here by these vertical lines, the magnitude of a vector. And then a unit vector is a vector of magnitude 1. So we divide by its magnitude to get a unit vector. We can take a vector that's not a unit vector, v, and turn it into a unit vector by dividing it by its magnitude. You learned these before when you first studied vectors, the laws of addition and subtraction. We occasionally need to do this. Addition is easy. We create this parallelogram, and the diagonal of the parallelogram is the sum of the two vectors. Or you can think of it as A plus B. Okay? Subtraction is just adding the negative. So in order to figure out whether it's pointing, whether the subtraction of A minus B points in the direction I show here or in the opposite direction, you can get it right every time if you take A and add the minus of B. So the negative of B is this vector. And when you add two vectors, you connect them tail to head. And you'll get the correct one. A minus B versus B minus A. Now, we can multiply. Once we've gone, scalars were easy. There was commutative, associative, distributive laws. But now with multiplication with vectors, we have different kinds of multiplication. We have multiplication of a vector by a scalar and multiplication of two vectors with each other, which can either be the scalar product or the cross product. So that's where things get a little bit more complicated. Multiplying by a scalar, I'm putting my scalar as this quantity alpha. It can be a variable or a constant. It's commutative, so I can put scalars anywhere in an expression, and I'm going to be doing that constantly, moving the scalars around. Associative, it doesn't matter what order you do these multiplications at all. And distributive, we'll do the distributive law all the time. You can multiply this individually by, first by v and then by w. Now the scalar product of two vectors is the dot product. Again, I know you know this already. You learned about it first as VW cos theta, or as the projection of one vector onto the other. I know I learned it that way. If you dot this vector, you get the projection of the vector in the direction of the other one. We can use the dot product to get a magnitude. So here, if we dot two vectors together, we get the square of the magnitude. If we then take the square root of that, we get the magnitude of the vector. Okay, so this dot product here gives us the square of the magnitude. The square root gives us the magnitude there. We'll use that plenty of times. Now, the dot product has these rules of commutative, associative, and distributive too, but associative doesn't work. You can't dot three vectors together, but they do commute. Okay, the dot product does commute, and it does distribute. Okay, so the z first dots with the v, and then it dots with the w. Okay, very straightforward. No associative law for the dot product. The vector cross product we won't use very much, but it will show up once or twice later on. Magnitude of the first, magnitude of the second, sine of the angle between them. And we have to use the right-hand rule to find the direction of the vector that results. The result of a cross product is a vector perpendicular to the first two. In the case of the vector cross product, there's no associative law, no commutative law, but there is the associative law and there is the distributive law. Okay, so no commutative law, just as a reminder. Okay, and now that was really warm-up material. Let's talk about the real stuff now, coordinate systems. So when we learn these rules in vector analysis, it's a math class, and maybe you use them in physics as well. But my experience is that in math class, when you're talking about these concepts, you learn techniques and you very quickly forget the physical meaning of these quantities. And in physics class, you very quickly go to scalar coefficients, writing the answer in a particular coordinate system, and rapidly forget that you were dealing with vectors. Okay? So in our case, we are going to be always very much aware of our quantities as vectors and of scalar coefficients and of their physical nature. So that's why we're going back over it, because we're going to be constantly dealing with vectors and tensors and linear vector products of vectors and tensors in order to calculate the appropriate things in rheology. Now, to actually do a calculation with a vector, we need to put it in a coordinate system. So one of the things that's true about vectors and scalars and tensors is that they are quantities that do not depend on coordinate systems. So for instance, if I lean on this table and push on it basically in that direction, but a little bit down and a little bit in that direction, there's a force that I'm putting on this countertop, and whatever force that is, it is what it is. But to write it in a coordinate system, it will change in how it looks depending on whether I pick a coordinate system that's maybe at this corner, a coordinate system at this corner, a coordinate system in the corner of the room, A coordinate system that's not right angles, those are legitimate and perfectly well used in rheology. Sometimes they're an advantage. Or even a coordinate system that's moving. Okay, you can even, in rheology, because we're dealing with plastics that are moving in space and very constantly deforming, sometimes it's more useful to have a moving and deforming coordinate system than one that stays put in the corner of the room. Okay? But no matter what coordinate system you pick, moving and deforming, the craziest one you want, this vector is physically a quantity that has a value and we're done. Just like, say, gravity. The vector due to gravity is what it is, 9.8 meters per second pointed towards the center of the Earth. If I write a coordinate system where one of the unit vectors points towards the center of the Earth, then that vector is 0, 0, g. But if I pick this coordinate system, then that vector is 0, 0, minus g. If I pick a coordinate system at an angle, it's some other which has components in two directions when I try to write that vector. So what coordinate system you actually write something in changes how it looks, but doesn't change the vector. Likewise, scalars, which don't have even direction, are independent of any kind of coordinate system you might be using. So what is a coordinate system for our purposes? A coordinate system is a reference that allows us to make calculations with vectors. Okay? And we can only use coordinate systems for three-dimensional space that are non-zero, three non-zero basis vectors that are linearly independent. Okay? So you had this also in introductory linear algebra. If you picked three vectors that are in the same plane, so for instance, in the plane of this table, if I picked three vectors that are in the plane of this table, obviously I can't write the gravity vector because there's no combination of the three vectors in this table, three pens in the same plane. There's no combination of those three vectors that I can use to get gravity because gravity is out of the plane. So that's why we have to have three non-coplanar or linearly independent vectors. So one of the things I asked you to do in the first homework was to show that three random vectors I picked out of the air might be linearly independent, and this is how you do it. Okay? Three vectors are linearly dependent if you can make a linear combination. There's a linear combination of the three vectors A, B, and C. And if you can find some value of alpha, beta, and gamma and get the linear combination to go to 0, then they're linearly dependent. And that's what's going on with these vectors in a plane, these three pens. If I put these the black one and the red one at right angles, then I can get the green one by adding this one and this one together and then normalizing the result. So let's say this is in the x, so the I unit vector. If this is one direction, let's call this one A, and we can call this one B, then I can get this one as A plus B, and then divide it by the magnitude of A plus B, and then it'll have the same length. So let's say this is a unit vector. Then this one would be that vector. I can make a linear combination of these two to get the third, and so they're linearly dependent. If I do the Cartesian coordinate system, so one is now standing straight up, there's no linear combination of A and B that I can do to get C, and so that one is linearly independent. So that's what I ask you to do in the homework, is to take the vectors I've given and try to make that linear combination. And all it involves is solving for alpha, beta, and gamma, and they should go to 0 if the unit vectors are linearly independent. Now in rheology and fluid mechanics, we have a common nomenclature that we use for making calculations with vectors, and that's what I'm introducing here. And this is a little bit different, perhaps, than you used in other classes where you've used vectors. You've probably seen this one, where you have a vector W, let's say, might have a coefficient in the I direction plus a coefficient in the J direction plus a coefficient in the K direction. So this would be the X direction, this would be the Y, and this would be the Z. And that's fine nomenclature. The only problem is it's not as easy as a numbered system for handling the kind of repetitive calculations that we need to do. So instead of using this IJK system, we replace this with the ones shown on the slide. I would write this as something times EX, EY, EZ, or coefficients times E1, E2, E3. So if I use the same values of the scalar coefficient, I shouldn't have used W twice. Let's use V. All three of those are three different representations of the same vector, but just with different nomenclature. And this one, with the 1, 2, 3, is going to be the one that's most useful to us. Now, these coefficients in the front are scalars. So these coefficients in the front are the scalar coefficients of the vector W with respect to, so WRT, with respect to the coordinate system. And in this case, it's the XYZ. X, Y, Z coordinate system. So there are coefficients for every vector that tell you how to form that vector in a given coordinate system. So going back to me leaning on this table here, this vector is what it is. It's a certain magnitude of force, and it's at a certain direction, and it's a constant. If I write it in this coordinate system, it will have a certain set of scalar coefficients. If I write it in this coordinate system, they'll be a little different. If I write them in this coordinate system, they'll be a lot different. And if I write them in a moving and deforming coordinate system, they'll be functions. They'll still be scalars, but they'll be functions. Because, you know, if it's moving, then at every moment, the coefficient of this constant vector will be a little different. Okay, that's very complicated, and luckily we're not really going to get there. So you don't have to worry if that gives you indigestion. Okay? But that is part of advanced rheology. So back to the slide, the rule is that any vector may be expressed in any coordinate system, in any valid coordinate system. So any vector may be expressed as the linear combination of three basis vectors. Valid basis vectors means non-zero, non-coplanar. So just that rule, just that sentence, any vector may be expressed as the linear combination of three non-zero, non-coplanar basis vectors, that rule implies this equation right here. Okay? A is any vector. Linear combination is of three vectors is here. Here are the three vectors, EX, EY, EZ. Linear combination from the previous slide, linear combination was some number times the vector plus some number times the second vector plus some number times the third vector. So here we have some number, which is just a name, times the vector we're interested in, times some number times the vector, times some number times the vector. And this is your familiar vector, column vector or row vector of coefficients. This nomenclature, which you're familiar with in our usage, is just a shorthand way of saying that this coefficient goes with this unit vector, the first one, the x1. This coefficient in a linear combination goes with the second. and this coefficient goes with the third. So then you can see why I like the numbers better if you go to the second line here. This XYZ is okay, but that required me to write a lot. If I write them as 1, 2, 3, I can be even more compact and write them as the summation j equals 1 to 3 of a sub j, e sub j. Now it turns out in continuum mechanics we're even, in some sense, lazier than that, because we're going to drop the summation sign. So for instance, when I write the product of two vectors, I can write it using this kind of nomenclature or this kind of nomenclature. But what I'm going to aim to in the next couple of slides is showing you a kind of notation called Einstein notation that Einstein himself actually used, where I can manipulate this expression by itself without the summation sign and get results for various calculations. Okay. So on this slide, this next slide, I show a trial calculation, but rather than looking too hard at that, let's leave that just as something you have in your notes, and let's look and do the calculation ourselves so you can see what I want to show you. So we have any vector, so let's say v, may be written as the linear combination of 3 non-zero, non-complanar basis vectors. So as soon as we say we have a vector, we can write this. We have a vector, it can be written as a linear combination of 3 non-zero, non-coplanar basis vectors. Now I'd like to be able to carry out some of those calculations that we introduced, ways of multiplying vectors and scalars. So actually, let me start by multiplying by a scalar. When I multiply by a scalar, we can figure these things out by really just invoking the very formal rules that I discussed a minute ago. So this is alpha times v, and I can write v out. And I can use the distributive rule. So this distributes. And because scalar multiplication commutes, I can either write this as alpha v1, or I can write it as v1, v2 alpha. I can move the alpha in a different position. Or I can write the alpha at the end. It doesn't matter, because the position of this alpha commutes. These are both scalars. And so they commute very nicely. So that's pretty obvious. You knew that before probably, because you knew that if you had a vector 1, 6, 7, and you multiplied it by 3, that you would get 3, 18, 21. That's all we're doing. When we have dot products, so v dot w, it works the same. We can write any vector as the linear combination of 3 non-zero, non-coplanar basis vectors. So we just rewrite this expression by writing those out. So this is 1, 1, 2, 2, 3, 3. And the rule for multiplying these out is, again, the distributive law. So in this case, this quantity multiplies each of the 3. This quantity multiplies each of the 3. And likewise for the E3 quantity. And that's where we get this enormous mess on my slide here. So here in my example on the slide, I have AB, And so here I've written A in an arbitrary coordinate system, B in an arbitrary coordinate system. I distribute A1, E1 across these three. That's this line. I distribute A2, E2 across these three. That's this line. I distribute A3, E3 across these three, and I get this line. And then when I multiply them all out, I get 9 terms. Now, you may be thinking, why doesn't she just eliminate E1 dotting with E2 because they're 0? And that's true if we choose the basis to be orthonormal. Okay? And that's an important distinction. And that's something that you're used to because up till this point, you've always used coordinate systems that are orthonormal. And we will too. For 95% of the time, we will also use coordinate systems that are orthonormal. So this is, in fact, going back to linear algebra class or your introductory vector class. This is the reason, this slide in itself is the reason we choose orthonormal coordinate systems so that we can simplify these expressions. And we can simplify, for instance, this expression A1, E1 dot B1, E1. Again, formally using the rules of associative and commutative law. A1, E1 dot B1, E1. Being very formal about it, these are scalars. Scalars commute, which means I can put them anywhere. So that means I can pull them out front. So there they are out front, out of my way, and that's my usual way of performing this kind of calculation is to move my scalars out of the way. And then I carry this out, and if they're orthonormal, in an orthonormal coordinate system, E1 dot E1 is 1 because they're unit vectors. E1 dot E2 is 0 because they're perpendicular. And E1 dot E3 is 0 because they're perpendicular. And also E2 and 3 are dot to 0 as well. So on the slides again, if we choose a basis to be orthonormal, which means mutually perpendicular and of unit length, then the dot products in multiplying two arbitrary vectors simplify, and all those 9 terms, which are very cumbersome and difficult to deal with, simplify to this very, very simple expression. You know that simple expression as well because that one is just saying if I have a vector A, which might be 1, 6, 3, dotting with a vector B, which might be 2, 1, 4, we know that we just multiply these two together. We multiply these two together, and we multiply these two together to get the final result. That's the same as A1, B1 plus A2, B2 plus A3, B3 is equal to A dot B. So multiplying vectors together, dot product, we can write it now in this way. It's familiar to you, but it's going to be less familiar when we use tensors, which will be the next step. In order to simplify that kind of operation, the operations that we do with the more complex systems, we're going to introduce a notation called Einstein Notation, which is a system of notation that only works for Cartesian coordinates. It works for coordinates that are orthonormal and constant. So Cartesian coordinates are orthonormal and constant. So what we saw on the previous slide was that A dot B was A1B1 plus A2B2 plus A3B3, which we could write as the summation of AJ, EJ, summation 1 to 3. Or if we drop the summation sign, we can just write it as AJ, EJ. Or if we had chosen instead of J as the indexing variable, AM, EM. Of course, the choice of J or M is completely arbitrary, so these two things are the same thing. And we're not writing the summation sign. So how do we know there is a summation sign? The way we know there's a summation sign is if there's a pair of like subscripts that are, if there are two of them, if there's a duplicate of like subscripts, there's a missing summation sign. Now, back here on this slide, we were talking about orthonormal multiplication and how if you multiply a vector with itself, you get the unit vector, or you get the value 1. If you multiply an orthonormal vector with one that is perpendicular, one of the other basis vectors, you get 0, etc. We can generalize this rule using the Kronecker delta function. So that's what we say here. Okay? In an orthonormal coordinate system, because the basis vectors are mutually perpendicular and of unit length, when you dot two vectors of like subscript, you're going to get 1. When you dot two unit vectors of unlike subscript, you're going to get 0 because they're perpendicular to each other. So that's just this Kronecker delta function. Delta function delta IP is a function whose value is 1 when the I subscript is equal to the P subscript, and that function is equal to 0 when the I subscript is unequal to the P subscript. And that's exactly the story here. So what we see is that this Kronecker delta function allows us to write A dot B directly. A dot B in Einstein notation, we write the A as AI, EI, leaving out the summation sign. Dotting it with BJ, EJ, leaving out the summation sign. And we already know the result. What's the result of dotting these two vectors together? Forget this notation, just go back to this. You know what this is equal to. What's it equal to? Right. A1, B1 plus A2, B2 plus A3, B3, right? That's the answer. Which we know that has to turn out to be, if we go back into summation mode, that's the summation of A, let's say K, B, K equals 1 to 3. Or in Einstein notation, that's AK, BK. But we can skip all this by just dealing with this format by first moving the scalars out to the front to keep them out of our hair. And that leaves us AI, EJ dotted together. And using the fact on this slide that when you dot two vectors, you get the delta function with the subscripts equal to the subscripts of the two unit vectors. So this is equal to AI, BJ, delta IJ. But we can further simplify, because what does the Kronecker delta function mean? It says this quantity is equal to 1 when I equals j, and it's equal to 0 when I unequal to j. That means I and j are redundant, right? We don't need both of them. In this expression, when I equals j, it's there. But when I is not equal to j, it becomes a 0. So we just throw it out. So what I usually say in my head to get the math right is I becomes j. Or j becomes I, but you just pick one, okay? And so if I becomes j, then I get aj, bj, and that's my final result. A dot b is aj, bj, which is correct. Okay, that's exactly the result we got. We have it with j's instead of k's, but that's irrelevant. We can take summations and change that subscript to whatever letter we like. So that is summarized on this slide. The big, hairy calculation of A dot B, where we write A with respect to this coordinate system with its coefficients, and B with respect to this coordinate system, this orthonormal coordinate system with its 3 coefficients. And we do all this distributive law business, get all 9 terms, allow like vector, a vector where it's 1 and 1 to give 1, 1 and 2 to give 0, 1 and 3 dots to 0, 2 and 1 dots to 0, 2 and 2 dots to 1, 2 and 3, etc. And we get this result. Or we can do it with the Einstein notation. We write arbitrary vector as aj, ej, where the choice of the j is arbitrary. We write the b. The rule is you must pick a different letter. If I pick the same letter, if I put j here and j here, I've not created this big mess over here. I've created something new that's not the right meaning. So you must pick a new letter. For every time it's an arbitrary choice, you must pick a letter that has not yet been used. And then you follow the delta function rule. Ej.em is the delta Kronecker delta jm. And then to get rid of a delta, you just say the words j becomes m or m becomes j, and you get the final result. Now, we can extend this to tensors, which I don't have my tensor slides, but tensors I'll be going over on Monday are the two-dimensional version of the vector. So for instance, a tensor would be written with 2 underlines, and it's the equivalent of a 3 by 3 matrix of coefficients. So a tensor would be written as a sum of what are called diatic products. It's a linear combination of diatic products. Where a diatic product is written as 2 vectors side by side. Now this is a new kind of multiplication to you. I can't imagine you've seen it before unless you've studied tensors before. In fact, when you've seen tensors before, like the stress tensor, this wasn't mentioned at all. Yet this is the math behind something called the tensor. The diatic product is a third type of product. We have this scalar product. We have the vector product. And now we have the diatic product, or the indeterminate vector product. The thing about the diatic product is that it doesn't simplify, okay? So it doesn't, unlike this case or this case, you can't say, well, it's the magnitude of the first, magnitude of the second, cosine of the angle between them. Or in this case, magnitude of the first, cosine of the second. Magnitude of the first, magnitude of the second, sine of the angle between them, and the unit vector. This one doesn't simplify. It's simply 2 vectors side by side. We can interpret this product in Einstein notation. as the same way that we have already. A, we can write as A, P, E, P. I'm just picking random letters for the subscripts. And put them next to B, K, E, K. And that's my diatic product. Now this I can expand. But again, I have to use my distributive, associative, and commutative laws to expand it. Okay, they're sitting next to each other. And these are summations, aren't they? Even though they're missing, this one is really A1 E1 plus A2 E2 plus A3 E3 sitting next to B1 E1, B2 E2, B3 E3, sitting next to. We can expand this by doing the distributive law. So for instance, this A1 E1 can be next to this one, then next to this one, next to this one. A2 E2 distributes, distributes, distributes. A3 E3 likewise. Distributes, distributes, distributes. And we're going to get 9 terms. Okay, 9 terms. So this is another big mess. Okay, so if we have A, B, that indeterminate vector product, we get A1 E1, and I'm distributing it next to B1 E1 plus A1 E1 next to B2 E2 plus A1 E1 next to B3 E3 plus A2 E2 times, it goes to the first one, B1 E1 plus A2 E2. Now it goes, following this green line, it goes to the second one, B2 E2 plus, again A2 E2, goes to the third one, B3 E3 plus, and there's 3 more. So in the case of tensors, or these 3-dimensional objects that we're going to be using, this Einstein notation is going to be very handy, okay? Because this is already boring, right? This is really dull to be trying to keep track of 1, 2, 3s and A, B, C's, etc. But we can learn how to do this manipulation using this delta function, this Kronecker delta, and the Einstein notation. That's going to be a snap. It's going to be very easy for you. And I'll actually do that full lecture next time, but let me motivate it for you. Let me ask the question, why take the time to learn these manipulations? And let me remind you of some Newtonian fluid mechanics. The Navier-Stokes equations, written in vector notation, is rho dv dt plus v dot del v equals minus grad p plus mu del squared v plus rho g. Okay? Del v is a tensor. This del squared v is del dot del v, and there's another tensor right there. So here's a dot product. Here's a dot product of a vector operator and a tensor. Here's a dot product of a vector and a tensor. The Navier-Stokes equations actually are the Newtonian version of the Cauchy momentum equation. The Cauchy momentum equation has the same left-hand side. But it has the stress tensor in it. The stress tensor. Stress is, in fact, a tensor, and it appears in the momentum balance. And in order to write constitutive equations that describe the motion and the stresses generated in fluids, especially non-Newtonian fluids, we need to be able to handle these kinds of calculations. So the reason we're spending this extra time is we're going to need to be able to evaluate things like the Cauchy momentum equation, the Navier-Stokes equations in multiple coordinate systems, and to understand what the rules of mathematics are that govern, for instance, what would be an acceptable form for this stress tensor. And what we're going to find later in the term is that there are rules of coordinate transformation that guide us in developing constitutive equations. For polymers and other non-Newtonian fluids. So our goal in this class in rheology is to figure out what that stress is as a function of velocity. And as written there, it doesn't make any reference to coordinate system, just like my vector force on this surface top doesn't make any reference to coordinate system. And we have to make sure that whatever math we use to put that equation, to put this stress expression into there, that it doesn't ruin this equation and all of a sudden make our math depend on coordinate system. And that's where we're headed. The Navier-Stokes equation, the Cauchy momentum equation, they don't depend on coordinate system. They can be written in any coordinate system. In your undergrad class, in fluid mechanics, you use tables usually of the Navier-Stokes equations to solve flow problems. It didn't matter whether it was in rectangular or cylindrical or spherical coordinate system or any coordinate system we like. And that's what we need to preserve. And so we're going to study for the next couple of lectures how to do these manipulations so that we can better understand what the constraints are on our equations in order to be able to write stress relationships that don't violate these rules. Okay? So starting on Monday, I'm going to go back and start with the lecture slides on tensors. And we're going to learn how to apply Einstein notation to tensors. Just a little bit harder than doing it with vectors, and then move on and start seeing Newtonian fluid mechanics using this same kind of vocabulary. Okay, so that's it.